Okay, so now we're moving on to 6.2, classifying the elements. And after we have separated the periodic table into metals, nonmetals, and metalloids, we're going to further separate the periodic table into several different types of metals and several different types of nonmetals. You'll need a few different colored pencils or markers or highlighters to fill in your periodic table. Colored pencils work great, maybe around 8 or so colors. So the first column that we are going to color in is a group that is called the alkali metals. And it starts with lithium and is lithium's whole column. So that whole first column, right, with the exception of hydrogen. Hydrogen is not considered an alkali metal because it's not even considered a metal, right? Hydrogen has reasons why it belongs in that column. It has one valence electron like the other alkali metals, and it behaves similarly in some circumstances, but it's a gas at room temperature, it's diatomic, it has a lot of properties of nonmetals. So what are the properties of the alkali metals? Well, as I said, they have one valence electron. And of course, the number of electrons is going to influence its reactivity. Because alkali metals only have one valence electron, it can lose that valence electron real easily, and therefore alkali metals are very reactive. In fact, they're the most reactive metals. They will react really quickly in water and in air, and because they are so reactive, they don't exist as what we would say a metal or an atom. They don't exist with all their electrons in nature. You can find the alkali metals all over the place, right? Sodium, potassium, lithium. But they're always the ions of those metals, not the atom with all of its electrons. They're also very soft. They have sort of a texture of like butter so that you could actually cut a piece of sodium metal with a knife. It's not as hard or durable as like an iron or a lead or one of the transition metals. And now for the alkaline earth metals. The alkaline earth metals, it sounds very similar to the alkali metals because they are similar to the alkali metals. The alkaline earth metals are the second group in the periodic table, the second column of the S block, if you remember from last chapter. Beryllium, magnesium, calcium. They're called the alkaline earth metals because a lot of those elements are found in minerals that would be found in rocks in the earth, things like calcium and magnesium. They are very similar to the alkali metals in that they're reactive, but they're not quite as reactive as the alkali metals. They're soft, but they're not as soft as the alkali metals. And that's because they have two valence electrons. So they will give up those two valence electrons, but not as easily as the alkali metals give up their one valence electron. And now we get to the transition metals. The transition metals are the D block metals. These are the metals that we think of when we think of metals. This is our nickel and our iron and our copper, silver, gold. These are the metals that when we think of metals as being shiny and lustrous, this is what we think of. Even though, you know, sodium and potassium and magnesium are also that way, we mostly see those in compounds. These transition metals we can often see as their atoms with all their electrons. So the entire D block here. And the transition metals we could classify as the most stable metals. There's two other classifications of metals: the inner transition metals, which consist of the lanthanide series and the actinide series. The inner transition metals are the F block metals. So those F block metals are together called the inner transition metals. And the top row of that starts with the element lanthanum, and that's called the lanthanide series or the lanthanoid series. And the bottom row starts with the element actinum and is the actinide series or the actinoid series. What can we say about them in terms of properties? Well, these, you start getting into elements that are created. Everything after uranium is an element that was created in a laboratory that doesn't exist on the planet Earth. They're called transuranium elements. And so because of that, they are sometimes very radioactive. Those would be the actinide series. So the inner transition metals together, that's that F block. And the only real property that we can say that all of those have is that they have irregular electron configurations. The electron configurations that we would have predicted for them in the last chapter are often not true. Those orbitals are so close in energy levels that you may have different orbitals filling in different orders. So we could just say irregular electron configurations. And then specifically the actinide series, that bottom row of the F block, those are all radioactive. That means that those nuclei are very large. The strong nuclear force is barely holding it together. And eventually, the electrostatic force will push the electrons away from each other, and those elements will decompose into other elements. That's what radioactivity means, is that the nucleus of a uranium atom won't stay together forever. Eventually, it will break up into smaller and more stable nuclei. It will become different elements. And now we're moving on to the nonmetals. So how can we classify the nonmetals? Well, the next group that we're going to look at are called the halogens. The halogens start with, there we go. The halogens start with fluorine. It's fluorine's group. We know that fluorine's group all have 7 valence electrons. And because of that, they're just 1 electron away from a full outermost energy level. And because of that, they are very reactive. They're the most reactive nonmetals, and in fact, they only exist as diatomic molecules. Think of what that word means, diatomic, 2 atom. You never find just an atom of fluorine floating around. You can find the ion, fluoride, or if you have fluorine gas, it's always 2 atoms of fluorine bonded together because they're so reactive. And the other piece of that is that they can be any states of matter. So iodine is a solid at room temperature, bromine as a liquid at room temperature, where chlorine and fluorine are gases at room temperature. So unlike all the metals that are always solid at room temperature, with the exception of mercury, all of the halogens have all 3 different states of matter in them. And then we get that final column on the periodic table, the noble gases. And I can't quite say that all the noble gases have 8 valence electrons because helium only has 2. But they do have their outermost energy level, their outermost energy level is full. With helium, it's 2. With all the others, it's 8. What that means is that they're very stable and they don't react with other elements in nature. So they're non-reactive. And all that leaves us now is hydrogen. Hydrogen we leave as a category unto itself. And the reason is that hydrogen, fits on top of the alkali metals. It has 1 valence electron. It can give up that valence electron just like all the other alkali metals. So in some ways, it makes a lot of sense that it's there. But in a lot of ways, it could also probably fit right above fluorine as well. It's a non-metal, like all the other elements on the right-hand side of the periodic table. It too, like all of the halogens, exists as a diatomic molecule. So hydrogen gas is always H2. So hydrogen is sort of in a category unto itself. It's like a non-metal, but it can also sometimes behave like a metal. Because of that, it's sort of unique. It's also 75% of all the atoms in the universe are actually atoms of hydrogen. And then the very last way that we can classify elements is by this idea of the representative elements. If you hear that word representative elements, you may also hear them called main group. It's just another way of saying the S and P block elements. Oftentimes when we're talking about reactivity or we're talking about something that we're going to learn called periodic trends, we'll sort of skip over the transition metals because they are all somewhat similar to each other, those transition metals. And then just looking back at this periodic table that we colored in, you notice that we left, right, a whole area of this periodic table without names of their columns. And some of them do have names, but they don't all have common characteristics. And that's because that staircase is running right through that section. So if I'm looking at carbon's column, carbon is a nonmetal, but then underneath it are 2 metalloids, and then underneath that are 2 metals. So those are, we just can't say that they all have the same properties because we have that staircase where we're transitioning from metals to nonmetals in between there.